I work in a kind of a general area of finite volume methods, adaptive mesh refinement, software, high performance computing. And I guess if I apply these things to application areas, I look at problems in geosciences, natural hazards modeling. So I'm going to talk about all those things today. I got several collaborators over the years. People that I went to graduate school with, advisors, collaborators, people I'm currently working with. Over the years, we've had several students who have been working on these projects with me. 3 of them are, actually 4 of them now are PhD students in the program now. One of them is a former undergraduate student, Hannah, who's now a PhD student at Notre Dame. And Eric is a PhD student in Germany. And all are to some extent involved in sort of this, the project that I'm going to describe. Okay, so this is going to be annoying. We'll have to do that. All right. So natural hazards modeling. So this is just a variety of what we can consider natural hazards. Okay, things that, you know, a volcano erupts and spews a huge amount of ash in the atmosphere. Wildfire and smoke, we're all experiencing that now. This is a page from the New York Times that allows you to simulate the smoke from all these different fires. So my family has a cabin in the mountains right about here. So they've been closely watching this Calder fire, which is that sort of getting really close to South Lake Tahoe. Dam failure, not exactly a natural hazard, although the reason for the failure in this particular case, this was the Teton Dam in eastern Idaho that failed back in 1976, basically failed only several days after it was full for the first time. It failed because they built a big berm, and the berm of sort of it was a big dirt dam, and the dirt leaked, right? So anytime you ever built a dam in a stream and you washed that's exactly what happened. They're thinking about rebuilding it now. I'm not sure what their plan is. And then here's an example of a sort of several events happening together. A volcanic eruption causes a landslide. The landslide goes into the ocean and generates a tsunami. Okay, so those are just some of the examples of problems that I think about. So what's common to a lot of these problems? Well, they typically take place over long periods of time, okay? These are things that happen over, you know, hours, days, weeks. Smoke transport, they've been tracing that smoke in the atmosphere from the fires for several weeks now. Tsunamis take on the order of hours. Say a tsunami is generated, caused by an earthquake in the middle of the ocean, it might take, you know, 12, 14 hours to hit land. These are all spatially localized phenomena. That is, a tsunami is actually a really small, out in the middle of the ocean, a tsunami might only be a couple of inches high. And it's only when it gets really close to shore does it develop into a huge tsunami. And so, but we need to carefully track that small localized feature over the entire expanse of the ocean. Smoke only takes, you know, when we're modeling smoke, we don't know where exactly it's going to go. So we need to have sort of a big region to consider, and the smoke, but though may only be really localized. There's often detailed physics though at a small scale. We can't make too many approximations at the small scale, or we won't get the modeling right at the larger scale. And then these models are often based on physical laws that are governing sort of the conservation of physical quantities like mass, momentum, energy, and so on. And then numerical simulations can help us actually predict the impact of these events. Okay, well, I'm going to give you just a little bit of mathematics, nothing more than Calc 3. I think I'm going to change my graphic. So the idea here is that we want to model this smoke transport. Okay, this is actually the modeling of something like this. We might assume, for example, that we're not going to model the details of the volcano. We're just going to assume that the smoke appears, or the ash appears at the crater of the volcano, and then it's ejected into the atmosphere, and then it gets transported by winds. Okay, and we want to sort of see where it goes. So what we might do is consider constructing just a small box, okay? And we'll create boxes all over the entire domain, but let's focus on a single box. And if we had a way to, inside that box, there's going to be a certain amount of ash. And over time, what's going to happen is that ash will flow into the box through the edges, okay? And the mechanism by which it flows in is a flux. There'll be a flux of ash. And so ash will flow in from, say, a neighboring box into this box, and then it will flow from this box into the next box. And if we could somehow track how the stuff was flowing in across the edges, we could then have a pretty good model of what was happening at a whole series of boxes like this. So this is in fact, looks very simple, but this is essentially describes what I just described in words. The time rate of change of an integral quantity. So we'll think of this as a volume integral over our box C. So you might be more used to seeing a double integral here. I've just written it as a single integral over a two-dimensional domain C. So this is the total amount of ash in that box. Well, how does the amount of ash increase? Well, it increases if flux, and then now I'm going to integrate around the boundary of the box. Okay, so I'm going to take a flux and go up the left, across the right, down the bottom, or maybe I go the counterclockwise, doesn't matter. But in any case, I'm going to integrate around the box this thing we call a flux. And notice I dot the flux with a normal derivative because we want the flux in the direction normal to the edges. So I integrate all the way around, slap a minus sign on it because the way that if we didn't have the minus sign, positive would be a flux that was leaving the box. Okay, but this is a quantity that's going to increase. So we want to know how much flux enters the box. Okay, so this is what we call a statement of conservation, basically. The only way that something can increase in the box is if it comes in through either side. So then we can do a little bit of math. That derivative on the outside, we can move into the inside because we're different. We're integrating with respect to x. So time is like a constant. Remember Calc 3. On the right-hand side, we can replace that boundary integral with a volume integral by applying Gauss's divergence theorem from Calculus 3. And then we can move everything to the left-hand side, put big brackets around the ddt that we moved inside, the divergence. This term here replaces the f dotted with n. Again, this is the thing you learned in the last week of Calc 3 that nobody ever remembers until they see it again in an upper division course. And then we set the whole, and then because we moved everything to the left side, we have a 0 on the right-hand side. And then we say, well, you know what, though? This should work for any C that I have in my domain, any volume, anywhere. So therefore, if this integral is going to be 0, this expression here had better be 0. Okay, and this is what we call a partial differential equation that expresses our conservation law. Okay, so this is what we call a conservation law. It's a particular kind of equation. I haven't said anything about what F is, and I'm not going to say too much about what F is, although I'll give you an example. But what is Q? Well, Q is any variable that we consider to be a conserved quantity. Sometimes in engineering, I think they use the word extensive quantity. It's a quantity that increases as the domain size increases. So for example, if I have mass and a little volume, increases. If I make the volume bigger, I get more mass, typically. So this is the sort of thing we think of as anything that we can integrate and get a sort of a quantity that depends on our size of the domain. Momentum is a conserved quantity. Heat is a conserved quantity. Internal energy, enthalpy, entropy, Gibbs free energy, all these mysterious thermodynamic quantities. Vorticity, so rate of spin, is conserved. Entropy, if you're into climate science, you may have heard of entropy. It's the integral of the vorticity squared. And then various tracer quantities. Ash, smoke, pollution, moisture, all those things are what we say conserved, right? We don't create ash unless we're right at the crater. Once the ash goes into the atmosphere, we assume we don't lose any ash unless we have a particular mechanism for destroying the ash. Things that are not conserved are things like temperature, pressure, concentration, or color. The temperature in a room, if it's doesn't increase if I increase the size of the room. Of course, heat may flow and cause the temperature to go up or down, but temperature itself is just something we measure at a point. Pressure, same thing, concentration, color. If I put some dye in water, it turns the water red, regardless of how much water I have there. Okay, so that's kind of the basic type of equation that I think about. Here's just a diagram. So I talked about one control finite volume, C, and I imagine but then I imagine a whole grid of these things, and I imagine fluxes going in, and then going in the box and out of the box at both the left and right edges and the top and the bottom edges. So I imagine 4 fluxes around the edges in this box C. And I imagine that my grid cells are enumerated. This is cell ij. So here's I down this center, J goes up, and this is cell ij, for example. So this might be cell 1, 1. This might be cell MM, if I have M by M grid cells. And then we can discretize our finite volume. So the thing that we're going to now replace, we're going to replace this integral with the average value of our Q over some finite volume Cij. And then I'm going to create an update formula that looks like this. The average value at a new time step is equal to the value at the old time step minus the sum of the fluxes around the boundary. Okay. I wouldn't worry too much about these signs or this here, but again, this is the flux that is leaving from the right edge minus the flux that's coming in from the left edge. Minus sign here makes, it turns that into a positive value. And these are the fluxes at the top and the bottom. And here, what is this thing? Well, this thing is an approximation to this quantity, this F, which is kind of mysterious. I haven't said anything about what F is, but along one of the edges, I average the value of the flux along one of the edges. Okay, so that bottom step there, computing that bottom step turns out to be actually the hardest part of this whole problem. Partly because how am I going to do this if I don't know what Q is? I'm trying to find Q, right? I don't know what this is. How am I going to compute this thing? Well, that turns out to be a problem that lots of smart people have spent their entire careers solving, okay? But it all boils down to a formula that looks about like this. So is this computationally expensive? Well, we can solve a PDE as a coupled system of, you can think of it, and this is actually not a bad way to think of it. You can think of it as a whole set of ODEs. You've all had like differential equations. Some of you may probably even had PDEs as well. I don't know how many of you have actually done numerical PDEs, but if we think of this as being a whole system, you know, you've probably in a differential equation course, you solve a system of 2 ODEs. You know, those phase field diagrams where you have U1 and U2 and they're coupled. Well, here we have a system of coupled ODEs, except that now instead of 2 of them, we've got an ODE at every single grid point. So we've got m squared of these things. So on an m by n grid, we have m squared ODEs to solve simultaneously, and this gets to be really expensive. Okay, so this is why these calculations are taking up all the supercomputing time that we have. This is the reason the DOE is spending millions of dollars on huge supercomputers like Summit and Aurora and Stampede. There's a whole bunch of them out there. They keep coming out with a new one every year. NSF also spends lots of money on supercomputers. And this is one of the types of problems that people spend their time on. So this is, of course, just a 2D calculation. Now imagine I had a whole cube. I would have m times m times m. If m is, say, 1,000, we're looking at 1 billion ODEs that we need to integrate. Okay, so here's just a quick example. A system of equations called the shallow water wave equations. They're commonly used to model what we call shallow geophysical flows, such as tsunamis, storm surge, debris flows, landslides, and so on. This may not look quite like the simple conservation law I showed you, but here we have a vector, h and hu, ddt of that vector, and here I have my divergence operator. So this thing in here is a flux. H times u is a flux, and this strange operator here, which is basically represents the transport of the momentum, plus something like a pressure term, is another flux. Okay. So what are the things we're tracking? We're tracking the height of a water column, and I'll show you a picture in a minute. The velocity, g is the acceleration due to gravity, and b is the bottom topography. So often here's, for example, an example of the type of flow that this might simulate. Here's a shallow geophysical flow, and here's another shallow geophysical flow. And you can see here that the bottom topography actually varies, and that's what that B is on the right-hand side. Here's another example. Here's a tsunami. Okay, so this is a long, thin, this goes all the way out to here. So even though we don't think of the ocean as shallow, it's very shallow relative to the extent of the ocean. And this varying bottom topography here is what really makes the tsunami really steep as it gets close to the shoreline there. So this B here is this bottom topography. So here's just a drawing. So we have some characteristic variables. There's our height. So the height is what we say that the height of the water column. We have a bottom. The depth is so we imagine that this line here is sort of sea level, and our B is the depth below sea level. And we have sort of a free surface height. And so here are some parameters, which in the shallow water model take on particular meaning. So for example, the ratio of this height, this characteristic height, this H0, divided by a length scale, which is the sort of the extent of the ocean. So the depth divided by the length is going to be really, really small. That's what this, double less than equals less than 1 means. It means really small, not just small, but really, really small. And so this is the kind, we'll track the water in these little columns here. Okay, so now I want to say a few things about, so I was going to show you a cool picture. Okay, so this is a cool picture. So, so I'm actually teaching my class, my numerical analysis class is happening, or numerical methods is happening right now. And last week when I first started the course, normally I would show them a few cool pictures, get them excited about numerical methods, and I told them they had to wait. So those of you who are in here, thank you for waiting. And and now I'll show you the cool picture. So this is an example of So you have to picture this as being water in a square pond. Okay, so we got a square like this room. Square pond has got solid walls on the side. And in the middle of the room, I put in, the water isn't, the surface isn't flat. In the middle, I have kind of an initial sort of hump of water. Okay, you might wonder how physically, how would I make that happen? Well, I don't know, you had a fountain or something that shot some water up at time 0. And now you just let the thing go. Okay, and of course, what you sort of expect is it's going to create kind of rings that go out, and then it's going to hit the walls, and it's going to reflect back. You know, if you've thrown a rock in the middle of a pond, it hits the outer edges of the pond, and it sometimes reflects back. So, and then this can kind of create some cool patterns. Okay, so this is that shallow water equations I just showed you. So those are the ripples going out, and then the reflections going in. And the colors are indicating depth. So yellow is the highest level, and then the darker blues are more shallow. So what do you notice here? Well, you notice that initially it looks sort of like you might expect. The rings kind of expand out, then it hits the walls. But you notice that there's lots of these sharp, really sharp discontinuities. Right? So for example, we could pick any one of these things. Whoops, I want to stop. I want to stop, I guess I have to hit stop. There we go. Okay. So you notice here that these are all pretty sharp edges. Nothing's getting really smeared out. This is like a nice sharp edge here. And in between those sharp edges, you notice there's lots of sort of where it appears like nothing much is going on, like it's really flat, okay? And that is basically what's going on. So you have these regions where you have like a really sharp discontinuity. Okay, again, a really sharp transition between, say, this shallow area and this, or this is going to be the shallowest, and this is a little more shallow. This is a little deeper, and this would be the deepest part right here. If we had a 3D, if I had shown you actually the surface, it would look like, you would see like straight like a prism coming out right here and right here, okay? And so you would see kind of these sharp edges moving in and out. That might be a cool, maybe I should try to visualize it like that. Anyway, so you see, okay, well, let's see now, if I have to have a little tiny box for every one of these things, is this going to be a very efficient way to calculate this? Here's another example. So this is water in a bowl. So you can take a bowl, fill it with water, and now just go like this. And the water's going to slosh around, right? And so that's exactly what this is doing. So here we have an example of something with bottom bathymetry, where the bathymetry is actually curved. And that surface, it's sloshing around, but that surface is staying flat. Not flat like the same height, but it's flat, but tilted. So this is so now you just think real quickly, if you were to be looking straight down on this, what would you see? It would look like a circle that was just going around like this, right? And you notice that the yellow is always at the top. So obviously the yellow is the high edge and the blue is the low edge. So that yellow is the part that's higher. Okay, so let's just take a look at the resolution here. So if we zoom in on this tiny little piece right here, this is basically, you can see these little squares, and those are what we call the finite volumes. Those are those little squares that I was showing you with fluxes around each one. Well, this particular simulation was done on a 1024 by 1024 grid, or about 1 million, basically 1 million ODEs to solve, just for that one little 2D simulation. Okay, now you might ask, do we really need this much resolution? Look what's going on in here. There's basically nothing happening in here. Okay, it's all one value. This is all one value. This is all one value here. Okay, this is effectively constant. Why do I need to take this, put this much resolution in an area that's constant? So then, well, it turns out we don't. Computationally, what we would like to do is we would like to add adaptive resolution. So for example, here, notice what I've done is that I have these squares here are bigger than the squares here, and these squares out in the middle are bigger than those squares. Okay, so each square is about half the size as I get closer to an edge. So wherever I have an edge, I have fine resolution, and where I have nothing going on, I have coarser resolution. And this is really going to allow this to become a much more efficient calculation. We call that adaptive resolution, or adaptive mesh refinement. I'll show you a picture here. So here's the same code, but with the meshes. So now you see that what we're doing is we're adapting the meshes to follow those sharp discontinuities and not wasting too much time in region, hopefully not wasting too much computational effort in areas out here where we don't have much going on. So how do we do this? I mean, I don't know, maybe you guys look at this and go, yeah, that doesn't look that hard. You just have to create all those little boxes and follow the edges. And well, it turns out that there's a fair amount of effort goes into developing a code that does this. Here's the slosh problem again. And let's take a look. This is this is viewing from the top. You can see the high area is this yellow area. The straight lines indicate that it's really staying flat. And what you see are a bunch of boxes that are moving with that circle. And inside of each box is a small grid. And that's how, in fact, these calculations are all done. So this is what we call adaptive mesh refinement. And in this case, we're doing it using a quadtree. So this is we take a domain, we subdivide it into 4, subdivide into 8, 16. So 2 by 2, 4 by 4 is 16, 8 by 8 is 64. And that way we can create finer and finer meshes here. These, you have to imagine one of these boxes cut in half. So four boxes inside of here. If I showed them here, you wouldn't see anything, okay? So that's why I don't show that finest level. But in fact, in the interior is where we have the finest resolution. So we call this adaptive mesh refinement, or AMR. It's a technology that aims to make efficient use of computational resources by dynamically adapting a mesh to follow the solution features we care about. So here we just care about the water. Here, in fact, there's nothing happening. It's completely dry, so nothing is happening here. So we only want to follow this water as it goes around. There's a number of numerical challenges. How do we develop solvers that can work on this kind of code? How do we, on these semi-structured meshes, how do we manage the overhead costs? We would also like to port this to multi-core machines, GPUs, shared memory platforms, and we would like users who have their own legacy code. So a user who knows how to solve a problem on a single grid, they would like to be able to take that single grid code and turn it into something like this. Okay, so I spend a lot of time thinking about what sort of interfaces do we need to allow a user who shows up with their single grid code and says, I want to make it adaptive. What do I do? And so I spend a fair amount of time thinking about how to make that process easy. So this project I've been involved in is called ForestClaw. It's a parallel adaptive library for logically Cartesian, so Cartesian is that little grid you saw, mapped multi-plot domains. It relies on a highly scalable library called pforest for doing all the grid management. And I'll show you a few pictures of what I mean by mapped multi-block. I like to think it's modular so that users can extend it with their own solvers. And it's based on an existing algorithm by Berger and Oliger and Colella, developed in about the early 80s. So you can go to my GitHub site and get some information on ForestClaw. Here's just a few details of this code. Well, it's written in C, C++, and Fortran. What's interesting here, it's got several extension libraries for solving a variety of PDEs. So conservation laws, there's all different kinds of conservation laws, right? I showed you one, but depending on how we define F, we get a whole bunch of difference. We can serve all kinds of different quantities. And it's parallel, so you can run it on a distributed system with MPI, or you can run it on GPUs. And it's got some support for legacy code. So if you happen to be, if you're following the talk and you have a code that actually solves on a single patch and you're thinking, oh, wow, wouldn't it be cool if I could do this AMR thing? Well, there's a good chance that you'd be able to. So you should talk to me. Here's just some more examples. You could think of this as being something like smoke. It's like a smoke ring. Okay, when you take I don't want to say cigarette because nobody should smoke, but you imagine you have a match and it creates a smoke ring and then it goes out like this. Well, now imagine that you've sliced through that smoke ring. It might look something like this if you wrap that ring that goes all the way around. And here you can see the resolution that we're solving on. It gets really, it's coarse way out here where nothing's happening. And then in here, it's really fine where we have lots of detail. And sometimes we like to be able to solve on circular domains or a torus, that'd be cool, a sphere. So here's if you're solving, for example, ash transport on a globe on the Earth, you might need a way to solve on the surface of a sphere. So we can do that. High performance computing. So how many of you have ever run codes in parallel? No, none of you? Well, in fact, all your laptops, almost every laptop that's built these days has at least 4 cores, if not 8 cores. So in fact, you guys are all running in parallel. You just don't know it, right? But if you explicitly want your code to run in parallel, that takes a little bit of work. And here's an example. So here's for example, I think in fact I did this on my laptop, and I was able to, I had to tell the code to put these grids on core 1, these grids on core 2, these grids in pink here on core 3, and the grids in blue there on core 4. So this is this idea of distributing, so we can principle, this calculation should take 1/4 of the work if I run it on 4 cores than it did if I run it on 1 core. So if every core is, if I divide up the work among 4 cores, should be done in 1/4 of the time. We call that scaling. Does that really happen in practice? It can. If you're really good, you'll get good scaling. Here's the same thing on a sphere. Sometimes I want it, or on a disk. Sometimes I want to solve things on a circle, not just on a.
Is your computer? They're saying there's heavy feedback. So see when Zoom, yes.
Oh, I want to mute. Thank you. Oh, I do that. Yeah. Okay. Sorry about that. I thought maybe I had to unmute myself. Okay. All right.
Thank you.
So here's how we measure scaling. I say, okay, well, I'm going to solve 1 problem on 1 processor. I'm going to solve 4 problems on 4 processors. I'm going to solve 16 problems on 16 processors. How much time should each of those jobs take? Let's suppose this takes 1 unit of time. And now if I say I'm going to solve 4 jobs on 4 processors, how many units of time should that take? Yeah, it should still take 1 unit, right? increased the work by a factor of 4, but I've also increased the number of cores by a factor of 4. Now suppose I increase again up to a 4 by 4. Okay, and I have, so now, well, if I have 16 units of work on 16 processors, it should still take 1 unit of time. We call that a weak scaling. And here's the kind of results that we get. So we ran this on a big supercomputer, an IBM Blue Gene Q. And here's the results on 1 processor, 4 processors, 16, 64. The perfect scaling would be a straight line across the top. And you see that we get pretty good scaling until we get down to 65,000 processors. And then it starts to drop off a little bit, okay? And you can kind of see what's going on. Well, at 65,000 processors, you know, things are just really far apart, okay? And so we, you know, you typically see that, okay? Now, of course, modern computers, you hope to be able to get up to a petaflop, say 200,000 cores would be nice. You know, if you can scale up to 200,000, you're doing really well. So we consider this pretty good. So we would say we've got good scaling up until about 16,000 cores. Here, we want to know all that overhead. I've got all these boxes. I'm managing all these boxes, you know, they all have to talk to each other, and that must take like all the time, you know. Wouldn't it be better to just solve on one big grid? And then you don't have all that communication. Well, it turns out that all that overhead is only taking about 10% of the time until we get up to about 16,000 cores. And suddenly we are spending a bit more time in overhead. And you'll see this blue thing is really where we're spending most of the time. And that's all the communication between boxes. So let me just show you a few examples of where we've used this code to really speed things up. This was we took a single grid code that was, it was a serial single grid code. Okay, it solved it in this big cube. And we took it and divided it up, did our adaptive mesh refinement. This is the transport of volcanic ash. It was an example of a volcano in Alaska. And so we took that single grid code and we said, well, let's see if we can make it adaptive and parallel. And this is the kind of speed up that we got. The original code took about 2 hours. So when I say it took about 2 hours, it took 2 hours to create this simulation, basically on a single grid. Okay. So here's the ash starts out about here.
Alaska or Mount St. Helens?
Well, okay, so this picture is Alaska, and this picture is Mount St. Helens. Yeah, so this is Mount St. Helens here. So so I didn't do this simulation. I did the Mount St. Helens simulation, and so that code took about 2 hours. And then when we did it on 2 processors, it took about 1 hour, 4 processors about half an hour, 16 processors, we got it down to about 15 minutes. And then when we included adaptivity, we actually that already on just 1 processor, by making the code adaptive, we actually cut it from 2 hours down to 1 processor, or 2 hours down to 1 hour, even on just 1 processor. And then from there, we actually see pretty good scaling. And so this takes about 15 minutes, the parallel adaptive version. And what you see, this blue line here, this is basically the numeric solver. All this other stuff is kind of the overhead associated with doing the adaptive mesh. So we're not really spending all that much more time doing the adaptive meshing. Some of you may have heard of implicit solvers. So elliptic problems require solutions to big linear systems of equations. So this is a project I've been working on with 2 students. Or Scott Ayton, he was a former student. He's not a student anymore. He's working actually as a BSU employee working on this project. He's developed a code called Thunder Egg, which is an iterative solver based on an algorithm called stabilize by CG with a multi-grid preconditioner. And this is an example in the bottom here of a solution. So on the left, we have a right-hand side, and on the right, we have an actual solution. You can see that what the boxes are all clustered where we have regions of high curvature in the solution. And then I have another student who's working on a similar problem, but using what's called a direct solver. So Damon Chipman is another PhD student working on a different kind of solver for the same problem. I've been looking at these shallow geophysical flows. So here's an example of a tsunami. But the interesting thing here is that you see these ripples. And those, in order to get those ripples, which are more realistic than just the straight shallow water equations, we solve something called the Sarah-Green-Nogby equations. And what I've illustrated here is that our 2D solver is giving the same results as a 1D code that I had. And here's an example of how we were using this code. So I have a student, Hannah Spiro, who worked up with me on a simulation of the flooding of the Teton Dam. So the Teton Dam was up here somewhere. It flooded basically into all of Rexburg. So Rexburg is up here off the page slightly. Here's Roberts. Here's Idaho Falls is down here. This is the Snake River. And up here is Henry's Fork, I think. If you're into fishing, this is a popular fishing area. But basically in 1976, when the Teton Dam failed, all that stuff got wiped out, created about $11 billion in damage. Another student of mine is working also with the same code. We'll be doing GeoClaw extensions to ForestClaw. And he's going to be looking at tsunami simulations and their interaction with the atmosphere. This is a recent project I've been involved in called AtmoSense. And the idea is that we're going to use the atmosphere as a remote sensor. So the atmosphere, you know, it's you don't think of the, but I think you're all familiar with the idea that if I clap my hands or something, a pressure wave is sent through the atmosphere and you hear it, right? So that's a signaling process. The atmosphere is acting as like a wire, okay? It can transmit information. Well, what happens if I have a tsunami down here in the ocean? Well, even though the tsunami is really small, it's going to cause a reaction in the atmosphere. And down here where it's, you know, the atmosphere is pretty dense, we might not sense it. But as we get higher up into the ionosphere, that's going to create a huge disturbance. That tiny little wave is going to create a huge disturbance in the ionosphere. And we can actually detect that. And that could be used as a way to detect earthquakes, tsunamis, before they actually happen. Okay, so it could be, it's sort of a way to do remote sensing that could be even faster than what, for example, right now we rely on buoys out in the middle of the ocean. You know, a buoy bounces up and down, and unless we're like monitoring the buoy or then hoping that the buoy didn't break or sink or lost its wire, you know, lost its Wi-Fi connection, we might not recognize that an earthquake happened out in the middle of the ocean. But this sort of using the atmosphere as a sensor would allow us to actually recognize this. So this is a project that I've been working on with a faculty member at Embry-Riddle in Florida. And again, Scott Ayton, who is a former BSU student who's working with me, Brian Kenyo. These are Jonathan Sively's slides. And here they're using ForestClaw now to do all these simulations, to develop a code called Magic Forest. So here's the atmospheric, here's a disturbance down here, and here's how it propagates up. And this is the sort of thing that we want to be able to detect, are these disturbances in the upper atmosphere. And just recently, Jody and I have started a project on tracking wildfire smoke. So we're going to solve, hopefully I'm saying this right, because this is kind of more Jody's area of expertise, is Euler-Lagrange equations for 4D VAR data assimilation. And the computing challenge is actually solving a forward and backwards problem for the inverse modeling using full AMR. And we've got, so Jody and me, and then Patricia and Sandra are both PhD students who've just started this year on this project. So we really only just had our first meeting. And this was funding is from NSF. And then, so I think that's pretty much all I wanted to say. I guess the big sort of push now is to really get a full 3D version of ForestClaw, because we need to have 3D for all these projects. And so far we've got what's called an extruded mesh. So you take a 2D mesh and just extrude it upwards so that we actually can solve in 3D, but we don't yet have full Quadtree refinement.